Alright, thanks for watching, and today I want to show an amazing fact about limit points. Namely, the set of all limit points of a sequence is closed. Here's what I mean by that, but first let me remind you what a limit point is. So let Sn be a given sequence, so we fix Sn today. Then S is a limit point, or a subsequential limit, of Sn if you can find some subsequence of Sn. So if there is a subsequence Snk of Sn that converges to S such that Snk goes to S, as k goes to infinity. So because we're trained to do that, let me motivate this with trains. So suppose you have a sequence Sn, so a train that doesn't necessarily converge. Then a limit point or a subsequential limit is a number, or plus or minus infinity, such that there is an express train converging to S. In other words, S is a limit point if you can find a subsequence Snk that converges to S. So in other words, a subsequential limit or a limit point is just all the possible destinations of express trains of Sn. And in general, there are many of such limit points. And in fact, we can now consider the set of all such limit points. And we'll call this capital S. So let capital S be the set of all limit points. So all the things of Sn. Sn. So here, capital S is all the dots here. And the thing is, so the point is, this set capital S isn't just a random set. It turns out it has a nice property which is called closed. And I will elaborate more on that when we'll do section 13. But all that closed means is that if you have a sequence in S that converges to some number, then that number is also in S. So, fact. So again, S is closed, meaning that if, let's say, Tn is a sequence in S, and one little technicality, technically infinity and minus infinity are in your set, but let's just assume your sequence isn't plus or minus infinity. We don't really know what convergence of stuff with infinity, and moreover, Tn converges to some number t, again, which could be infinity or minus infinity, that's fine. Then what we want to show is that t is in S. In other words, it's closed under limits, if you'd like. Namely, if you consider this set S, and you have a sequence Tn, so T1, T2, up to Tn, that converges to T, then it turns out that limit is also in your set. Okay, and let's prove this. So the proof is really neat. So here's the thing. Again, suppose so I'm not going to use n, I'll use k for reasons that will be apparent very soon. So suppose tk is a sequence in S with tk converging to t, and our goal is we want to show that t is in S. Okay. Now what is going on? So remember what S is. It's the set of all destinations of express trains. of your sequence. So this is S, and we're assuming, again, that's kind of tough, we're assuming we have a sequence in capital S. So a sequence of limit points, T1, T2, Tk, and we assume this converges to T. Now here's the thing, T1, well, it's a limit point. So what we know is there's a subsequence that converges to T1. In particular, so what this means is there's a subsequence that is as close to T1 as you want. So, in particular, there is some element, let's call it Sn1, that is at most 1 close to T1. So again, since T1 is a limit point, again, there's a subsequence converging to T1. So in particular, there is Sn1 with Sn1 minus T1 is at most 1 away from T1. But then you can continue. You see, T2 is a limit point. So there's a subsequence converging to T2. Meaning there's another term, let's call it Sn2, that is even closer, let's say at most 1/2 away from Sn2, so from T2. So since T2 is an S, there is Sn2 with Sn2 minus T2, it's less than 1/2. And by the way, we can choose Sn2 to be after Sn1 because there are infinitely many terms actually that are at most 1/2 away. So that's not a problem. And in general, you see, because Tk is a limit point, there must be a subsequence converging to Tk, so there is some Snk that is at most 1/k away from your Tk. So since Tk is an S, there must be at least Snk, again after everything else, with Snk minus Tk is less than 1/k. Now, okay? Get it? Here's the thing. What we want to show is that T is a limit point. So we need to find a subsequence that converges to T. And here's the beautiful thing, and this is sometimes called a diagonal argument. Well, we found Sn1 that's close to T1, Sn2 that's close to T2, Snk that's close to Tk. Well, now consider this diagonal sequence, Sn1, Sn2, Snk, and we're actually claiming that this goes to T, whatever that means. Okay, look, this beautiful diagonal thing. Now, so consider the sequence Snk just formed by all those numbers, Sn1, Sn2, dot, dot, dot. And then we're claiming that Snk converges to T, but we just have to be a little bit careful because it's possible that T is infinity. So we just need to separate our cases. So case 1, suppose a T is a real number. And then let's compare Snk with T. Then, so Snk minus T. Well, here's the thing. We know Snk is close to Tk. So we can just use this beautiful triangle inequality trick. So subtract and add Tk. Tk, Donkey Kong. And we get less than or equal to Snk minus Tk plus Tk minus T. But now, by construction, we know Snk minus Tk, it's less than 1/k. So this becomes less than 1/k plus Tk minus T. Okay, but here's the thing. Well, 1 over k, that goes to 0 as k goes to infinity. And remember what was t? Well, we assumed that tk converges to t. So this also goes to 0 as k goes to infinity. So if you want by the squeeze theorem, what we get that Sn k goes to t. Goes to t. Which is good, which means because there is a subsequence of Sn, namely Snk, that converges to t. So t is a subsequential limit. So t is a limit point, which is what we wanted to show. And then for the other cases, it's similar. So if t is infinity, well, we can't use this triangle inequality trick anymore because we can't compare Snk and infinity. But here's the thing. We still have Snk minus tk. It's less than 1 over k. So in particular, Snk minus tk, it's bigger than minus 1 over k. So Snk, it's bigger than tk minus 1 over k. Okay, 1 over k, that goes to 0. But then what do we know? We know tk goes to t. So in this case, what we have is tk goes to infinity, because that's what t is. So this goes to infinity, and then by comparison, we get Snk goes to infinity. So Snk goes to infinity, but then what do we get? We get a subsequence that converges to infinity. So infinity is a subsequential limit. So infinity, which is t, is then an s. And then we're done. And lastly, if t is minus infinity, the case is similar. So you may say in this case, the case is closed. All right, thank you very much.